Good afternoon, everybody, and a very warm welcome to the SESAR Young Scientist Award Ceremony 2020. My name is Peter Hecker. I'm the chairman of the award board, and it's a real pleasure to have you here today. You are aware that the SESAR joint undertaking is advertising every year an award for young scientists. So this year the call was published again, and very good and excellent proposals have been received and evaluated. And today we want to give the floor to the best 3 2020 applications, and then finally at the end announce the winner. So what is the background? The background is that the SESAR Young Scientist Award aims to recognize young scientists who have demonstrated excellence in air traffic management and aviation-related research fields. The award also provides researchers starting out in their career with an opportunity for further professional development. In addition, the objective of the award is to showcase their potential, the potential of the young talents to formulate fresh ideas and solutions to the challenges facing ATM and aviation. The award contest is open to any scientist at every level from bachelor via master's degree up to a PhD working in the specific fields I just mentioned. And all applications are going to be evaluated along the criteria scientific excellence, obviously, then the impact, mainly through publications, the level of contribution to internationalization and researchers' mobility, and finally, connecting to stakeholders and building networks. All the applications have been evaluated by the award board, and the award board consists of 3 members from the SESAR Scientific Committee. And I'm very happy that Rita Somogi from Hungary and Patrizia Marti from Italy supported me in this job so that we all together had a view on the applications and selected the most promising candidates. We received top quality applications, very exciting topics, convincing solutions, and very sound thesis material. And we unanimously agreed on a shortlist with 3 shortlisted applicants. And those applicants now are invited to attend the SESAR Innovation Days 2020. And this is where we are right now. And I would like to call the 3 shortlisted candidates on the stage in alphabetic order. And the first one is Eulalia Rodriguez Sanz from University Seville. Hello, Eulalia. Then we have Alvaro Rodriguez Sanz from Madrid University and Christian Verdonk from Cranfield and Madrid University. So it's a great pleasure to have you here, and you all will now have the opportunity to present your thesis and your work. And the first one will be Eulalia Hernandez Romero, and I'm very happy to listen to your contributions. The word is yours, Eulalia.
Hello, this is Eulalia Hernandez. I am very happy to be presenting my research this afternoon. First, I would like to thank the Young Scientist Award Evaluation Panel for selecting my application as one of the 3 finalists. So thank you very much. It is an honor. I am very grateful for the opportunity to present my research in front of you today. So my PhD thesis is titled Probabilistic Aircraft Conflict Detection and Resolution under the Effects of Weather Uncertainty. It was conducted at the Department of Aerospace Engineering at the University of Seville in Spain, and my advisors were Professor Damian Rivas and Dr. Alfonso Valenzuela. So the topic of my research is the problem of aircraft conflict detection and resolution, but from a probabilistic point of view. So what motivates this work is the necessity of managing and integrating uncertainty in future decision support tools for ATM. In particular, we are focusing on the problem of conflict detection and resolution, which is a very important task in ATM. It is performed by air traffic controllers, and it is essential to ensure safety in aircraft operations. So conflict detection and resolution relies heavily on trajectory prediction, and we know that the trajectories of the aircraft can be very, very sensitive to the effects of uncertainties. That's why future conflict detection and resolution decision support tools must manage and integrate the uncertainty present in the air traffic management system. Among the many sources of uncertainty that exist, this study focuses on weather uncertainty. And we know that weather uncertainty is a very relevant topic in ATM research right now, because we realize that this uncertainty can affect the aircraft operations quite a lot. So taking this into account, the main goal of the thesis is to develop a probabilistic framework for aircraft conflict detection and resolution under the effects of weather forecast uncertainty. So this is an overview of my PhD project. We have developed a methodology that takes as an input both the aircraft flight data and the weather uncertainty data. The weather uncertainty information is provided by probabilistic weather forecasts, and in particular, we are using a forecasting technique, which is very popular. It has proven to capture the uncertainty in weather predictions very well, and it is ensemble prediction systems. So an ensemble prediction system is a collection of forecasts, also known as members, that tries to constitute a representative sample of the potential states of the weather outcome. The hope is that the true final state of the atmosphere falls within the ensemble spread. So using these two inputs, the flight data and the probabilistic weather data, we have developed a probabilistic trajectory predictor, which is able to compute the aircraft trajectories, but also it can capture the uncertainty in those trajectories. So we use two different approaches. The first approach is called transformation approach, in which we transform the probability density function of the weather variables into the probability density functions of the trajectory variables. And the second one is called ensemble approach, in which a deterministic trajectory predictor is used for each one of the members of the ensemble to obtain an ensemble of trajectories. So after the probabilistic trajectory prediction is done, the next step is probabilistic conflict detection. A conflict between two aircraft exists when a minimum separation between the aircraft is predicted to be smaller than a given separation requirement. And in probabilistic conflict detection, the minimum separation between the aircraft is computed as a random variable, and we are able to obtain the PDF of this random variable, and also we are able to compute the probability of the conflict. And finally, after the conflict detection phase, the final stage is the conflict resolution. The objective of probabilistic conflict resolution is to generate resolution trajectories for the aircraft that lower the probabilities of the conflict below acceptable levels. So these are the applications that were studied during the thesis. First, we studied the problem of en route probabilistic conflict detection. We consider two aircraft flying two-dimensional level flights and a time horizon of 20 minutes. The next step, we expand the conflict detection methodology by introducing three-dimensional flights, and we are doing so considering descending trajectories in the terminal maneuvering area of an airport. The next steps now introduces the conflict resolution methodology. We are going back to the two-dimensional trajectories, but now we are considering multiple aircraft. And finally, the fourth application goes a step further by considering both conflict detection and resolution, but now for three-dimensional trajectories, hundreds of aircraft, and we expand the time horizon up to 60 minutes. So now I'm gonna introduce some of the results that were obtained for these four applications. So I'm starting with en route probabilistic conflict detection for two aircraft. In this problem, we studied two aircraft flying in the same airspace with two-dimensional converging trajectories, and we consider a time horizon of 20 minutes. The source of uncertainty is the horizontal wind, which was obtained from ensemble prediction systems. The results of this study look something like this. The probabilistic conflict detection methodology computes the probability density function of the minimum separation between the aircraft, and the probability of conflict can be then obtained. We can do this for a different range of traffic scenarios, and also for different levels of wind uncertainty. So if you want to know more, the findings of this study were published in these two publications over here. So next, we expand the probabilistic conflict detection methodology to include three-dimensional flights, considering the standing flights in the terminal maneuvering area of an airport. The methodology was tested using standard arrival routes in the Denver airport in the US, and the wind data was obtained from the high-resolution rapid refresh forecast from the NOAA administration. And I must say that this work was the result of a research visit at the National Center for Atmospheric Research in Boulder, Colorado, under the supervision of Dr. Matthias Steiner, and also with the help of Dr. James Pinto. And during this research visit, I learned a lot from the experience of the people at NCAR about weather forecasting and the impact of weather in aviation. And of course, I tried to include everything I learned in my PhD thesis. So these are some of the results that were obtained. We were able to develop a probabilistic trajectory predictor that considers horizontal winds that were altitude dependent. And we were able to obtain the probability density function of the minimum separation between the aircraft, as well as the probability of conflict. The results of this study were published in the 2018 International Conference on Research and Air Transportation. And the next application now introduces the conflict resolution methodology. We consider multiple aircraft flying two-dimensional en route trajectories. The time horizon is still 20 minutes, and the wind uncertainty is again obtained from EPS. For this application, we used an example of traffic in the south of Spain, where 4 aircraft approach a common navigation point. These are some of the results that were obtained. In these figures on the left, we can see the predicted trajectories before and after the conflict resolution. And I must mention that the conflict resolution problem was solved as an optimization problem, where the objective function was to minimize the deviations of the resolution trajectories from the nominal trajectories, while also maintaining the probabilities of conflict below a given threshold. So in the figure on the right, we can see the probability density functions of the minimum separation between all pairs of aircraft. And the dotted line at 1 represents the separation requirement, so that we can see that the PDFs that fall to the right of the separation requirement are pairs of aircraft that are in fact in conflict. In the figure over here, we can see the PDFs after the conflict resolution, and we can see that the pairs of aircraft that were before in conflict now have a PDF that is to the right of the minimum separation requirement, so the conflicts have been solved. And again, this work was published in these two publications over here. And now I'm going to talk about the final applications, which is three-dimensional strategic conflict detection and resolution. Now we consider hundreds of aircraft flying three-dimensional trajectories in the same airspace. We consider trajectories that are this one shown in the picture, which over 800 trajectories at the same time. The time horizon has increased from 20 minutes to 60 minutes. And also we are not only considering the uncertainty in the wind, but also we are considering temperature of uncertainties, which again are going to come from ensemble prediction systems. In particular, we're using the Cosmos 2 EPS. So the conflict resolution again is tackled as an optimization problem. And because we are now working with hundreds of aircraft, the number of decision variables of the optimization problem is very, very high. That's why the optimization problem is not suitable to be solved with traditional optimization techniques. And for optimization problems like this with a high number of free parameters, techniques based on meta-heuristic have proven to be very useful. And we use this kind of algorithms to solve this particular optimization problem. And this study was partially carried out in a research visit at the École Nationale de l'Aviation Civile in Toulouse, under the supervision of Dr. Daniel Delahaye. And it was very helpful to obtain the help of the team at ENAC about optimization in ATM, and it helped me a lot to integrate efficient optimization techniques in this particular conflict resolution application, and also to be able to do it in an efficient way. These are some of the results we obtained. In the figure on the left, we can see the nominal trajectories of the aircraft and the detected conflicts. In blue dots, we represented the conflicts that have a low probability of conflict, and in red dots, we represent the conflict that had a high probability of conflict. So you can see in the picture on the right that the aircraft resolution trajectories after the conflict resolution process, and we can also see that the number of high probability conflicts has been reduced significantly. And finally, this work was published in these two papers in last year SESAR Innovation Days and this year's as well. So now I'm going to finish with some conclusions. We proposed and successfully tested methodologies for probabilistic conflict detection capable of statistically characterize the conflict between two aircraft, and also for probabilistic conflict resolution, which were able to generate resolution trajectories that lower the probabilities of conflict below acceptable levels. And these methodologies aim to extend the capabilities of current conflict detection and resolution approaches, and allows to being able to predict and solve conflicts with larger anticipation. And finally, I hope that this work is an early step for the future development of decision support tools for conflict detection and resolution that consider weather uncertainty data. And also I hope that it will contribute to reduce the negative impact of weather on the safety and efficiency of ATM. As future work, it can be considered the possible integration of different sources of uncertainty. For example, the aircraft departure times. And another future work could consider the application of the methodology to smaller, slower vehicles that can be heavily affected by the weather uncertainties due to their size, like, for example, small unmanned aerial vehicles. And last, I think it could be possible to use the proposed conflict resolution methodology as the base of a probabilistic storm avoidance tool. Treating the storm as non-cooperative agents to avoid, we can use the same optimization techniques that we use to solve conflicts between two aircraft to avoid interactions between aircraft and convective weather cells. And that's all. Thank you very much for your attention. And I will be very, very happy to discuss any questions or comments that you may have. So thank you.
Great, Eulalia. Thank you very much for this excellent presentation. I think it was very comprehensive. And before we join the questions, I have to apologize announcing you. I mixed up your name. So of course, the correct name is Eulalia Hernandez Romero. So apologies for that.
That's
so
fine.
I've received two questions so far. The first one is from Matthias Poppe, and I'm going to read it. Matthias is asking for 60 minutes look ahead. A lot of aircraft in Europe are still on the ground. Do you also consider uncertainties in time?
So I think he may have asked this before the section on future work. So no, this is something that we would like to add in the future, because I know that the uncertainties in the departure times can be quite significant and even overpower the uncertainties in the weather. So that's something that we will have to integrate in the future.
Okay, thank you very much. And there's a second question from Sebastian Wangnick, Eurocontrol Newark. And he says, hi, Eulalia, the spread of the conflict probabilities look very narrow. In particular, given that you look out for 20 minutes, how does it come?
So I not I don't know exactly know which picture or which particular data is Sebastian referring to, but some of the pictures that were shown, we were showing the conflicts, and the with the local higher time is 20 minutes, but the conflict can happen in a shorter time. So, for example, some of the figures that were shown in my presentation, the conflict took place at maybe 8 or 10 minutes. So it's normal that this spread of the separation between the aircraft is smaller than it would be in 20 minutes.
Okay, great. Thank you very much. So there is one more question. How do you think your work can support air traffic controllers?
So I think that it could be helpful for them in like two ways. First, there is also the probabilistic conflict detection methodology, which are the aircraft separation and the probability of conflict. Give the air traffic controllers an idea of the severity on the conflict and the probability. And this, I think, is very relevant information for controllers, and it can help them make better decisions. And this is one thing that it could help, but the second one is that the resolution of the conflict resolution phase can be used as a guide or a suggestion for controllers to decide on which separation maneuvers are going to be implemented. So hopefully that could help to reduce their workload. So in the end, the air traffic controllers will be doing the same as they're doing now, but they will be better informed so they can make better decisions.
Okay, thank you very much. So there is one more question from Sebastian, and I think then we should close the question and answer session. He is asking, I still find the spread very small when compared to real world uncertainties, for instance, also by climate noise. I understand you are considering only wind.
Yes, so of course, the aircraft are going to be affected by a lot of sources of uncertainty, and not only the wind, which is the one I'm considering. And I also consider the temperature, but even that the temperature has even a smaller influence on the aircraft trajectories. So of course, the uncertainty from other sources that I did not consider would make that spread larger. So what I tried to tackle is how, in particular, this uncertainty translates to the uncertainty in the trajectories and in the conflicts. But of course, if we want to look at real conflict detection for real applications, we will have to consider other kind of uncertainties. And I'm sure that's the subject of other research projects. And of course, I will be happy to learn more about that in the future.
Okay, great. Thank you very much for the excellent presentation and your discussion.
And thank you for all the questions. That was very interesting, and for letting me speak in front of all of you today.
Thank you very much. So we will now come to the next presentation. This was Eulalia Hernandez Romero, and now we will switch to the next one. And we are asking Alvaro Rodriguez Sanz to join the stage. And please, Alvaro, present your speech.
Alvaro, you're still muted.
Sorry about that. Sorry. Good afternoon. Thank you, everyone. Thank you very much for attending. I wanted to say thank you also to the SESAR joint undertaking for their consideration and for this opportunity. It's an honor and a great joy to be shortlisted as a candidate for the 2020 SESAR joint Scientist Award. Congratulations on the organization of this award and the SESAR Innovation Days. My name is Álvaro Rodríguez Sanz, and I'm going to present the main features of my PhD thesis, which is titled Uncertainty Management and Performance Optimization in Airport Operations using Probabilistic Reasoning and Reinforcement Learning Techniques. It was supervised by Fernando Gómez Comendador at the Technical University of Madrid. We will go through 5 main sections today: introduction and background, scenario and data characterization, uncertainty management, response optimizations, and conclusions. First, I will review the motivation for this study, its main objectives, its approach, and the contribution we expected to achieve when we stated the problem. As you may all know, air transport operations rely on a complex network structure where several facilities, processes, and agents are interrelated and interact with each other. In this large scale and dynamic system, airports are the interconnection nodes that help aircraft distribution through the network and act as a transport modal changers for passengers. Potential incidents, failures, and delays may propagate throughout the different nodes of the network, making it vulnerable. This could lead to system-wide congestion problems. So, moreover, uncertainty in operational conditions makes airside integrated operations a stochastic phenomenon. We need to understand the system behavior and its operational dynamics. It is required to develop tools to improve predictability and reliability by managing uncertainty and optimizing the operational response. In that sense, regarding the approach of the problem, we choose a dynamic spatial boundary associated with the extended terminal maneuvering area concept, which allows us to consider inbound and outbound timestamps. We focus on the tactical phase in order to consider the primary and initial inefficiencies of the system. The models proposed in this study can be parameterized and also adapt the results to the varying nature of the sources of uncertainty. Besides, these models are able to learn from new data. We follow a predictive approach, act when the system is providing signs of malfunction before it reaches degradation. And the inputs for the model construction and calibration will rely both in data and expert judgment. We expected to assess airport operations as an integrated architecture that includes the surrounding airspace. This is, we do not only consider the airport itself, but also the surrounding airspace. Our view tries to characterize the processes and link inbound to outbound flights in order to understand uncertainty dynamics. It implements the impact of stochasticity on prediction and considers the causal relationships between variables affecting performance. It moves to a multi-state view of reliability. It presents a methodology to optimize the system's response against uncertainty propagation, and it seeks the evolution from reactionary intervention to predictive interventions. When presenting my work, I always say that this is what we see when we look at an airport, but this is what we really want to manage at an airport. The main goal of the study is then to systematically assess and monitor integrated airport operations by using novel approaches, probabilistic reasoning and reinforcement learning techniques, to manage uncertainty in terms of predictability and system reliability and optimize operational responses. We will use weather, radar, and airport operational data, and also expert knowledge, applying reasoning and reinforcement learning technique to help airport operations and air navigation service providers to increase predictability, enhance operational efficiency, and improve resource allocation. We wanted to change the traditional view to a new perspective, where the airport is understood as a multi-stage system with different levels of performance, where airport and airspace operations are analyzed in an integrated manner, where different areas, delay, capacity, even environmental impact, are considered, and where we evolve from reactionary interventions to predictive interventions. Now, I will introduce you the scenario selected for the case study and the initial data characterization phase. We validated and tested our models at a major European hub airport, Madrid, and we had different data sources: weather, radar, operational information, delay causes. So the data preparation phase covered all activities required to arrange the final dataset from the initial source of information. We had to link the inbound and outbound movements, assessing their turnaround operation. The attributes included in the dataset were those related to airport infrastructure, airline, aircraft, and route characteristics, operational times, timestamps, and regulation, meteorological information, and performance metrics related to capacity and delay. As an initial step, we created a business process model related to the airport collaborative decision-making program. It acted as a framework to understand relationships among procedures at the airside and airspace integrated stage. This initial data characterization section gave us conclusions regarding the system behavior, and it also allowed us to recognize operational patterns. Particularly, it helped us to understand delays dynamics and the airport's level of saturation. Then we developed a model to manage uncertainty at airport operations. This model was structured in two analyses: a probabilistic graphical model through a Bayesian network approach to manage uncertainty and increase predictability while providing insights about factors affecting performance, precursors, and a multi-state system reliability analysis based on Markovian model to evaluate the system state as a degradation alert and understand the airport's dynamic. The first part, the prediction and causal analysis, has four main objectives: to identify factors influencing performance, to characterize uncertainty sources, to appraise the cross dependencies among variables, development of a causal model, and to predict outcomes given some inputs, the operational circumstances. It was developed through a Bayesian network, which relates through arcs and nodes the different attributes involved in the problem. It is a graphical probabilistic approach to manage uncertainty and assess decision-making. Bayesian networks allows cross-inference for deriving conclusions under uncertainty, where multiple sources of information and complex iteration patterns are involved. The final model considered 51 attributes with different natures. We included operational, meteorological data, infrastructure data, etc. A Bayesian network works by setting values at some nodes and deriving the probability of having the rest of the nodes in different states. Using forward analysis, we can predict. It is possible to estimate the final departure delay and the system's potential saturation, which can be used in the settlement of optimal turnaround and buffer time. It allows us to perform sensibility analysis. Using backward analysis, we can diagnose. It is possible to identify the main contributors, causes to a final delay. This can be used to locate inefficiencies, diagnose irregular operations, set performance target, and define actions, allocate resources that may correct the identified disruptions. The second part of the uncertainty management model consists on a reliability analysis. It has four main objectives: to model the airport operational dynamics, to establish a predictive framework regarding degradation, to cluster airport states, to find behavior patterns, and to develop functionalities of the reliability model: performance, time between failures, efficiency, recoverability, availability, etc. This model is developed through a multi-state system and Markov chains approach. The multi-state structure considers the different performance state of an airport system at different areas: capacity, delay, environmental impact, etc. We move from a binary work or not working view to a granular perspective. Meanwhile, the Markov chain approach allows us to foresee the evolution of the system performance at the subsequent steps, or in this case, operations. The transition matrices and the steady state vectors for the system blocks or areas, capacity, delay, environmental impact, etc., allow us to evaluate the airport performance. These matrices represent the one-step transition probabilities between states. We also analyzed the global performance matrix for the whole airport system and its evolution. Then, this leads us to the system dynamics. This methodology models the dynamical behavior of the airport over time. The probability of being in each state at a given step for a component is obtained from the Chapman-Kolmogorov equations. It also provided us with the evolution of different performance indicators and system functionalities: time between failures, efficiency, recoverability, availability, etc. Finally, we proposed a response optimization methodology. This approach is based on the combination of dynamic programming as a tool for solving optimization and optimal control problems by simplifying a complicated problem by breaking it down into simpler subproblems in a recursive manner, and reinforcement learning, which is a technique of machine learning concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. Our models are based on the idea that the output of the system is a sequence of actions as part of a global policy. The system evolves and there is no such thing as a best action in any intermediate state. An action is good if it's part of a good policy. This policy also changes the system state, so a feedback control approach is developed. We develop a methodology to manage turnaround times under party schedule allocation by also considering airport congestion and inherited delays. Therefore, when setting the optimal turnaround time, we consider not only outbound delay and buffer cost, but also the cost of perturbation in the schedule adherence, internal delays, and the airport level of congestion. It is a dynamic and adaptive model that can be used to support decision-making processes in balancing turnaround associated cost, improve departure time predictability, and increase the system robustness. We obtained feedback maps that display the optimal turnaround policy time as a function of both state variables, arrival congestion index and arrival delay. The numerical solutions of the method provide, for example, airlines with policy recommendations. This method allows us to obtain optimal policies that react to the state variables, allows us to appraise past strategies by comparing the real decisions to the optimal solutions proposed, and it may help airlines or airport operations to reach schedule adherence and improve operational predictability for departure times. Finally, the conclusions. By developing several models which are connected and can be used together or separately, the main contributions of the study are related to the identification of main factors that influence performance, the assessment of the quantitative impact of these factors, the uncertainty management by enhancing predictability and assessing the system reliability, and response improvement by searching optimal policies in the turnaround process. We have achieved our initial objectives by obtaining models that assess and predict operational performance at a tactical level, focusing on airside integrated operations. We use different inputs, appraise the relationship between attributes that affect performance. We provide a probabilistic approach to manage uncertainty and assess decision-making, which is consistent with the treatment of stochastic processes, using a predictive approach and generating tools for managing and visualizing uncertainty while optimizing the airport's response. The main limitation for the proposed models, which is part of the future work, is related to the fact that turnaround operations have been addressed as a single compact block, while direct benefits of the proposed models are enhancement of the system efficiency, improvement of the robustness in the presence of operational uncertainty, facilitation of resource allocation with multiple stakeholders, and development of a decision support tool that account for delay dynamics and behavior. To conclude, please let me say thank you to the journals and reviewers, congresses, research stays, and industry experts that have helped me through this path. Thank you very much for your attention. Here I leave you my email in case you want to contact me. Thank you very much.
Thank you very much, Alvaro, for this very clear presentation. And I've seen that there are already 2 questions. The first one again from Matthias Poppe. And Matthias is asking, have you calibrated your model parameters, for example, based on past data?
Yeah, we have calibrated, we created 3 subsamples. The first one was related to the construction of the models. The second one was related to the validation of these models, where we could test these parameters. And then we have the test subsample. In overall, in the validation subsample, we get a average error of around 10%, and with the test subsample, which was implemented in with data which was not used in the construction part of the model, we get like again a 10% error. So we think that the model was not overfitted. And yes, we used past data, and we also try to predict the future data. Thank you.
Okay, thank you very much. And the second question is from Sebastian Wangnick. Hi, Alvaro, have you identified in the course of your work the impact of the various features on the turnaround uncertainty?
Yes, I mean, regarding the features, as I presented, we took into account meteorological impact, operational problems, all this kind of infrastructure, the runway that it was in use, the terminal that was in use. So we were allowed to understand where some delay problems were detected. As I was saying, and part of the future work, we took the turnaround process as a block. which is okay to understand if the adherence to the in-block and out-block times is okay, but we need to develop it in a micro view to understand if the different parts of the turnaround process are going well or need some input in them.
Okay, thank you very much. I would have a question myself. You have presented in the middle of your presentation a matrix where you insert the probabilities of transferring from one state to another state. You wanted to measure the airport performance, for example, with that. So what is the typical dimension in a real case scenario of such a matrix?
In that matrix, we use this transition matrix that tell us in every step how the airport is changing. We use it one operation as one step for the different changes, and we understood that depending of the time, because it's not uniform, it depends if it's in a peak hour or in a valley, you can have between 15 or 20 operations to have a real change in the situation, depending on the block, because we have delay block, environmental impact block, but this was the amount.
Okay, thank you. And what do you think are the main practical applications for these models?
I think these models could be used by airport operators or air navigation service providers to predict the airport state, and in that way manage uncertainty, and in that way also allocate resources so delay is not propagated. But also it can also be used in a backward way. I mean, you can set a target for delay, for example, and understand what should be the conditions to achieve this target. So it could be a decision-making tool or even a resource allocation tool.
Okay, great. So what will be the next steps in your research?
We will need to test these models with other airports to gather more data, to implement new features. For example, in these blocks for the airport, we could use the economic development of the airport. And as I was saying before, we want to have a micro view of the turnaround itself.
Okay, great. So there is maybe a final question. Yeah, there's one question. For de-icing uncertainty, you would need another airport than Madrid, I guess. So that was the comment from Sebastian. Maybe you want to respond?
Yeah, for sure. I mean, the good thing is that we tested the model through the last 3-4 years, and as we were talking at the beginning of the session, surprisingly, we get 2 winters with snow in Madrid. So we get some meteorological impacts. But of course, we need another airports with different conditions to test the model for sure. Thank you.
Okay, so just to give us a complementary bit of information, before opening the session, we chatted, and Eulalia, who's currently in Sweden, told us that even in Sweden, in Linköping, there is no snow for the moment, so even that wouldn't help. So thank you very much again.
Thank you very much.
Thank you, very nice presentation, thanks a lot. And now we will come to the third shortlisted candidate, and that candidate is Cristian Eduardo Verdonk Gallego. And he is from Madrid University as well. And therefore, I would like to hand over to Cristian's presentation. Please go ahead.
Hello, my name is Cristian Verdonk Gallego, and I'm going to present my work on extraction of trajectory contextual factors and its application in trajectory prediction using statistical methods. I would like first to congratulate my fellow colleagues in this. I have also been nominated for this SESAR Young Scientist Award 2020. I would like to thank the SESAR Joint Undertaking and the panel for considering my application, and I would like to thank my supervisor Fernando Gómez Comendador and other very important people that have helped me throughout this research, like Paco Saez Nieto, José Miguel de Pablo, and finally my family. This research started in 2014 and finished in September 2020, and it was conducted at the Universidad Politécnica de Madrid. The motivation of this research was driven due to we had a need for determining the mental workload of the air traffic controllers, and with the models we were using at that time in CRIDA. the fact that two aircraft are entering into a conflict, and that is the driving action of an ATC clearance, has a really important weight in this model. So it was important to know if two aircraft were going to enter into a conflict, and if that was the reason for this ATC clearance. At that time, we took a naive approach, trying to propagate the trajectories and just determine if two aircraft were going to enter into a conflict. The problem was that we had a poor performance in our TPs, and then the identification was not reaching the levels that we wanted. So that was the motivation, trying to start and go further in the trajectory prediction. The aim of this research on a personal side was trying to develop more the domain on the ATM, statistics and programming, but about the research itself was to develop a trajectory predictor able to adapt to different contexts based on a systematic knowledge building from data exploitation and exploitation of ATC cognitive patterns. So for doing that, the first step was of the research, of course, was trying to do a literature review and finding some gaps that we were going to fill with our research. On the TP performance, it was identified a need that we needed to increase the performance of the TP in order to support the new services proposed by the new SESAR concept of operations at that time. And also that one of the gap was that one of the main factors is that the contextual factors were not sufficiently understood. On the side of the trajectories themselves, we saw that from the flight phases and the contextual factors that in the literature there are really good work, excellent work from the climb and cruise phases, and also in the Meteo as contextual factors. We could highlight the work of Aliger et al. Of the NAC, or the work of Manuel Soler and the team of Carlos III, and also the Universidad de Sevilla on the Meteo. But the gaps were about the descent profiles, and also what about the impact of operational factors in our trajectories. Finally, the traffic as a contextual factor is considered for strategic and planning purposes in ATM. We could see that we are trying to predict entry counts, occupancies, and so on, in order to determine the capacities and any action on the demand side. But when we are speaking about the tactical side of ATM, the air traffic control, we don't see that the ATC intent is considered enough when we are developing our trajectory predictor. So these gaps led us to define three research questions. The first one is, how can we exploit data? How can we also organize the data in order to enable us to conduct this research? The second one and the third one are about the impact of the operational factors in the descent profile of the trajectories, and also finally, how can we include the surrounding traffic as a relevant factor for our trajectory predictors. And all of that we were going to develop or apply the knowledge discovery in databases framework, trying to go from signals to knowledge. So the first thing that we have to do is to organize the data. We apply the data warehouse paradigm, trying to organize our problem, the trajectories and all the ATM in terms of dimension, spatiotemporal dimensions, and also operational dimensions, and the facts. This paradigm enables us to really go further, go beyond in the analysis of the different factors. We applied a methodology to a use case centered in a use case in a Spanish sector, in this sector that is in the Barcelona Air Traffic Control Center. So this sector is mainly driven by two flows that are, one is an evolution flow coming from the north of Europe and the British United Kingdom. Nor the flights are all the flights going towards the Balearic Islands. On the other hand, we have cruising flights from west to east, and these flows interact in the critical point of Barcelona. So, and in addition, the top of descent of these aircraft were most of them around this point. So, just a summary of the data that we have considered, more than 47,000 flights, 7 million tracks, and more than 200,000 interactions between the air traffic controller and the controlling working position. The first step that we did in trying to answer the second question, what are the operational factors impacting in the descent profile, was to do a fast analysis using multilinear level models in order to determine the preliminary factors in the descent, in order to infer or see what are these factors and the impact on the descent profile. Then we were going to apply this in different trajectory computation engines, trying to see different performance of these engines. So we applied 3 different computation engines, typical total energy model with the parameters given by VADA, also learning the thrust law, applying previous work in the literature, and finally using purely data-driven computation engines like neural networks. So we center our focus in the descent and the vertical profile. The findings, the most important findings, probably are that the most relevant factors that we consider and we found was that we feed our engines with the proper requested flight level and the flow of the aircraft, we were really improving the performance of our computation engines. And also the computation engines based on neural networks were giving us very good results in the training and in the testing phase, removing the bias and reduction of, we see a reduction of the variance regarding the total energy models. An important element to consider as well is that when we include the airline, the company as a factor, in the training phase we saw that it improved the performance, but when we went to the testing, we saw that the performance worsened because of reasons that could be, for example, the different cost index applied. Of course, we consider different neural networks for different aircraft models as well. So, having seen these 2 aspects relating to question 1 and question 2, the most relevant work we considered in this thesis was about the question 3, about how to include the surrounding traffic into the TP. Well, the last step in the research and this presentation is try to include the surrounding traffic as a factor for our trajectory predictors. So what we did was try to define a metric for identifying the air traffic interdependency, and then consider that as a precursor for ATC actions and therefore modifying the ATC intent. With this, what we did was then propagating the trajectories based on these new ATC intents. Of course, for the identification of the traffic interdependency, we consider the work conducted by Houston about the cognitive abstractions of the traffic controllers. First, we based all of our predictors, horizontal and vertical, on the standard flow abstractions that reflect the expectations of the traffic controllers. And also the critical points are crossing points between flows where we have high concentration of traffic. In addition, we consider that the safety nets are defined in time terms, for example, the time to the CPA. So what we did is to change actually the focus from where is going to be the aircraft at this given time to when are the aircraft going to arrive to this given point. If we do that change, what we actually can do is to define the interdependency based on a time-based separation metric. So we can actually define and find close formula for the gap time, and also at the end define the probability that 2 aircraft were going to arrive to a given critical point with a gap time below a threshold. So in terms of this metric, we define our interdependency. So also considering the performance of our trajectory predictor. So for giving you the sample, the use case that we studied is this critical point when we have potential interactions not only in the planet flight plan, but also in the recurrent ATC action. So you could see here two examples where the air traffic interdependency metric, the horizontal metric, gave us an alert when we were doing the predictions when the aircraft were entering the sector, and they gave an alert saying, okay, this aircraft may have a problem, and when we went to explore the vertical profile to see what had really happened, we actually see that the ATC has stopped the flight, the standing flight in the first case, and in the second it gave an early TOD. When we studied the whole sample, what we actually saw is that those aircraft that were in a conflicting situation were usually, they have more likelihood of being given with an early TOD, or the area around the critical point was completely removed from the options in order to give that clearance. So we saw that we could define this dependency between the position of the TOD and the metric in this specific case. So at the end we include all the factors and so on in order to try to identify the position of the TOD and therefore propagate the trajectories of the vertical profiles from that point. When we did that, we include the factors, but we still had a binary behavior on the residuals, and we look at that and we saw, okay, the only binary element that we have not considered included in our predictors was the runway configuration in Mallorca. That was the destination of this flow of traffic. And when we include that, we were able to completely characterize the residuals, and actually the inclusion of that factor into the predictors gave us the solution, and we had much healthier results on the residuals for the vertical profile. So just some conclusions: the data warehouse paradigm and having a good definition of the problem in terms of dimension facts in order to aggregate and also isolate the different factors is a key question, a key conclusion. Also the flow feature is something that we need to include in all the analysis. About the operational contextual factor impacting on the descent profile, we saw that the flow of their traffic was key in order to improve our TPs, and also that the neural networks were giving us good results, and so we could consider this approach in order to define new computation engines. Finally, about the surrounding traffic, what we saw is that the proposed time-based interdependency metric was actually being a precursor in this specific case for ATC actions, and also the whole TP based on standard flow abstractions and neural networks provide us very good results on the TP performance in the short time. So finally, at the end we have always new factors that we need to consider, and in this case was the runway configuration, the hidden factor. Well, we have published with this research specific 2 journals and 1 conference, apart from other research that we have developed in the last years. Finally, this is being also applied now, being matured in PG18 in the wave 2 of SESAR, and also in the project FAR. Well, thank you very much, and please we will answer any question that you have. Thank you.
Thank you very much, Christian, for this very clear and convincing presentation. And I already have seen that there are questions. The first question from Sebastian. Hi, Christian. Possibly ANSPs need rather 2 ATC TPs, one to manage the agreed flight path, the ATC clearances and the internal sector handovers, and a second one that tries to predict the as-flown trajectory and then to feed conflict resolution and other support tools. What do you think?
Well, indeed, now I'm working now at CRIDA, and I'm involved in PG18 in the Wave 2 Solution 53. And we are considering this research trying to provide likely trajectories apart from the one that is planned for the planning controller in order to provide him with more situational awareness of potential interactions that may appear because of a clearance in the previous sector, in the upstream sector. So yeah, I think that not only for the conflict resolution, but even we are working on this with the in the planning phase. So considering look ahead times of 12 to 25 minutes.
Okay, thank you very much. Another question I would have myself. Now, if you would have been forced to use only deterministic methods, conventional methods, so would you expect that a similar performance would have been achievable?
That is a very interesting question. One of the key elements that we needed to to understand that for our TP we wanted to use the data that was available at that time in 2014 when we had the data. What we saw is that when we use, for example, the total energy model, we need, for example, all the research that Eulalia has shown is basic for us, and we could, for example, try to infer these parameters from in this probabilistic on the wind, the temperature, but also the mass. But you need also the guidance mode that is going to be put going to be used by the pilot. So at the end, there are a lot of parameters that need to be taken into account. So when you use that deterministic only one configuration for the flight intent, for the aircraft intent, you may have a good prediction on those specific conditions. But what else? I mean, there are a complete myriad of conditions that could impact on your trajectory, and then the view that the system has is completely different than the one that the ATC is using indeed for controlling. So that is that is the situation. I hope that I have answered your question.
Yes, you did. Thank you very much. You made an interesting side remark. You referred to Eulalia's work. And that brings me to the question, do you see any relationship between what you have done and the work of the other nominees? So is there any links or interfaces?
Yes, indeed. I mean, when we conducted the literature review, we saw that the Meteo was actually has been addressed by a lot of, well, not a lot, but other researchers and so on. So we went on another direction. But the interesting point was that actually we took the same approach on giving a probability distribution for the conflict. Eulalia work focused on the distance, probabilistic on the distance. For example, also working with the work conducted by Irving. I'm sorry, I don't know if I have pronounced well, in 2002, that is now at Eurocontrol. But on our side, we have developed the time separation. So I think that these two together could provide more context, more information to the conflict detector, and that is of course something that we need to explore. In addition, Solution 53 Alpha now is in PG18, sorry, in SESAR, is considering all the impact of Meteo. And of course, the approach that Eulalia shown, I think it is quite remarkable, and we should try to follow it.
Thank you very much. Now, if you are targeting higher maturities, what could be next steps?
The next step, I try to, well, I have just mentioned that before, but now we are working in the PG in project 18 for the skies, and it is key for all our research to actually go to the ATC, to the air traffic controller, to the stakeholder, and try to understand their interests, and try to really see
how our research is going to impact on the system, something that is deployable, and that is a good lesson learned for me in this period that we are trying to mature this research. We need to define all the OIs and try to identify how our specific added value, I would say, can help the actual problems, and that is it goes a little bit beyond what is science, the scientific approach that we follow, but really understand what are the needs of the ATC.
Okay, thank you very much. So there are no further questions. Then we will close this question and answer session. Thank you very much for your presentation and the further elaborations. Thanks a lot.
Thank you.
Okay, now we've seen the three shortlisted candidates. We have seen Eulalia Hernandez Romero. We have seen Alvaro Rodriguez Sanz and Cristian Eduardo Verdonk Gallego. And now let's see who is reaching what prize. And you are sure, you know that there is the 5,000 euro check awaiting the first prize. Then there is the second and third prize, which is a 500 euro voucher, because this year no traveling is possible, and therefore the joint undertaking has decided to provide the equivalent as vouchers. And so let's go for the third place, and let's see who has reached it. Third place then goes to Eulalia Hernandez Romero. Congratulations, Eulalia. It was a great contribution and a very good presentation today. Excellent. So thank you very much. And we are very happy that you provided your proposal and delivered your thesis. Thanks a lot. Congratulations. Okay, then let's go for the second place. Second place then is with Alvaro Rodriguez Sanz. Congratulations. Excellent work as well. And thank you for submitting your proposal. We enjoyed it very much. And thank you. And so there's no big surprise anymore. And the winner then is obviously first place, Cristian Eduardo Verdonk Gallego. Congratulations. Excellent work. And maybe you all can come virtually, of course. You can turn on your camera so that we can see you, please. And yeah, I would have loved to hand over the check and the vouchers personally. It was always a lot of fun during the last years, and unfortunately we can't do this right now, but we do it virtually, and we'll send to you along with little other trophies you will get. And so we are very happy to see this great success of your scientific research. And that brings me to the final conclusions, and to everybody listening to this event. We are awaiting exciting applications next year again for the next version, the next round of the SESAR Young Scientist Award. So please consider and submit your applications whenever possible, and potentially we will see you next year here at the stage. Thank you very much. Have a nice day. And then I would like to hand over to the next moderator, and enjoy the rest of the meeting today. Thank you and bye-bye.